Hello, pre-calculus. Sorry I can't be at school today. My son is sick and can't go back to school yet. I will be doing a video for you today though, so we can stay on task for getting this unit finished before spring break. So we're going to talk about vocabulary that's calculus related that we use to describe graphs. We're going to use these to describe polynomial graphs, but really all or any type of graph we can describe using these concepts. So the first concept we would want to talk about for a function graph, or a function in general, is where the function is greater than 0 and where the function is less than 0. Where is the function have positive y values? Where does the function have negative y values? Oops. See if you write things right. And when you have a graph to answer this question, that's actually a very easy question to answer. Because when you're looking at a graph, you can see the positive y values are the places or happen when the graph is above the x-axis versus negative y values come in the section of the graph that's below the x-axis. Okay. When we describe these sections of graph, they're kind of going to be described using x values. Sort of think about them the way you describe a domain. So for this particular graph, I would say that f of x is greater than 0 on, and then these are intervals. We'll say it's greater than 0 from the interval 4, in this case 4 to 5, but if we sort of do this, maybe we just stick an arrow in here just for our note purposes, then this is more like a polynomial than 4 to positive infinity. I did not include the 4 because at 4 we're equal to 0 and I want just greater than, not equal to 0. We're going to do the same thing at the end here. We're going to ignore this point or cross it off. We're going to stick an arrow at the end here. So if you want to try this before I write it down, where is f of x less than 0? Be careful. We actually are going to have to look at this in two pieces. It's less than 0 from negative infinity up to the 1, and then from the 1 to the 4. Remember, we're not including where we're equal to 0. Okay? All right. That's an easy thing to do when we're looking at a graph. It's a little harder when we're not seeing the graph, but that's actually the last lesson we're going to do, is how do you figure that out, greater than 0, less than 0 for a function, without the graph and without making the graph. You don't actually need to make the full graph. You can collect some information about the function and answer the question without the graph, but that's next. So number 1, where are we greater than 0? Where are we less than 0? All about looking at above, below, x-axis. Pretty easy. Increasing, decreasing. This is the one we tend to confuse with greater than 0, less than 0. Greater than 0 is positive. Increasing is getting bigger. So the y's are getting bigger. So your y's don't have to be positive to be getting bigger. Two different ideas. So increasing or decreasing, this is more of an idea of describing the slope of the graph. What sections of the graph are have a positive slope, which means that they're increasing, versus more of a negative downhill slope, which is decreasing. And there can be sections where the graph is constant, neither increasing or decreasing. Not in a polynomial, but in a graph where you might have a piece that's perfectly horizontal. Oops, that doesn't look perfectly horizontal, but something like y equals 3, and I would be sticking my lines out. I'd be sticking my arms out if you were watching me live. Something like y equals 3, perfectly horizontal line, is neither increasing nor decreasing. So, where is my graph increasing? Where is my graph decreasing? Well, polynomial graphs go back and forth between increasing and decreasing. We don't ever have a level part, or they may be increasing or decreasing all the time. I would say this function is increasing on the interval from negative infinity to 1, and then from 3 to infinity. And then we're decreasing on the interval from 1 to 3. Remember, those are not ordered pairs. These are intervals of x values. So if I go back up to the graph, increasing, decreasing, increasing. Once again, easy to tell when you're looking at a graph. One of the things we learn to do in calculus is we learn to determine this without seeing the graph. So just from the equation, you can do things and figure out increasing and decreasing. The purpose of talking about these concepts in precalc is so you understand what the words mean. So then when we talk about, okay, how do you figure that out without the graph in calculus, you've got some background on the words. Okay? Increasing, decreasing, slope, positive, greater than, less than 0, y value. Y value positive, y value negative for greater than, less than 0. Y values getting bigger, y values getting smaller, uphill, downhill for increasing, decreasing. We have what are called either relative or local maxes and mins, maximums and minimums, when a function changes from increasing to decreasing. And a lot of times, peaks and valleys. You definitely looked at these at, a peak, like the top of a curvy part, or the bottom of a curvy part. It doesn't have to be curvy, but on a polynomial, obviously it will be. It's something you identified on the calculator when you looked at it. The calculator is great at it tells you maxes and mins. So this is, I don't think you'll have problems with. You just look at the graph. Once again, something we can do in calculus without seeing a graph. By looking at this graph, f of x has a relative or local maximum at x equals 1. F of x has a relative minimum at x equals 3. X values. It doesn't have to be the highest point on the graph, it just has to be kind of a high point in the neighborhood. So that's a max, that's a min. There are things called absolute maxes and mins. We differentiate between them in calculus for certain reasons. I'm not going to worry about that today. So maximums and mins, relative maxes and mins, we can have multiples. If we have a polynomial curve that's something like this, we're going to have a min here, and then a max here, and then a min here, and then a max here, and then a min here. You don't have to just have one. It's relative. It's not the biggest maximum. It's a maximum. It's the biggest one in the neighborhood. Okay, the biggest one of the points that are nearby. Okay. The top of the pile, bottom of the barrel. All right, last thing is concavity. Concavity has to do with the shape of the curve. So a curve that's curving more like that, which you can sort of picture as continuing in part of a U shape, we would call concave up. Concave up, like a cup. You can think about that and put a little handle on that. Right? That looks just like a cup. If the curve is more like that, kind of rainbowy, or if we continue that, helps you make the noise, then that's concave down like a frown. Concave down, oh, okay. This changes as a graph moves. It can go from concave up to concave down. So what we'll talk about for these graphs is at a particular point, how we would talk about the concavity. And let me grab this guy and exactly where I found it. It's always in the same place, but I never seem to be able to find it quickly. Oops, let's just grab him. Okay. So, for example, we're not going to describe all the concavity, but that's a little bit more complicated, and we really do need calculus to tell where the concavity changes. But if I pick a particular spot on the graph, let's say I picked that spot right there, that x. So like that's about x equals 3.5. I would say that the function is concave up at that section. It's a little more like, it's curved more like that. Versus maybe here, if I was looking at x equals 0.5, it's more of a concave down, where the graph is curving up that way. If I ask you this question, when I ask you this question, I'm going to pick a part of the graph that you can tell. I'm not going to pick like where it, there's graphs that we do like that, and right there you'd be like, oh, it's kind of changing. Yeah, I'm not going to ask you about concavity right there. Now, this is very clearly a concave up area. This is very clearly a concave down area. That's a transition point in between called the point of inflection. We'll use calculus to figure that out at another point in time. Point. Okay, so I'm hoping, and since now you have this on video, you can go back and rewind or re-listen and do this at your own pace. I'm hoping now what you'll be able to do is to try example 2. I have the key and I'll post it. I'm not going to write out the key in the video, but what I do want to show you in the video, because I don't know if I copied it this way. I don't think I did. Okay. I think I just copied that. Add some letters to some spots. Look at how I'm lettering this. I hope I didn't do this differently. Yeah, I think that's right. This is not an easy graph scale-wise. I pulled this from another source. So I've given some letters here to help you describe sections of the graph. So maybe, for example, let's do the first one. Where is my graph? Where is my function greater than 0? I would say my function is greater than 0 from A to B. Oh, I lied. Did you all go, no, that's wrong? A to C and E to G. Okay, try that. Pull the key up on Blackboard to check it. You have another review paper to do where you're going to practice this some more and some finding information and sketching graphs. We are probably not having the quiz Friday. I will put something out on Blackboard and email to let you know that for sure, but that doesn't mean you should be working on this because we are still going to test next week. All right? Behave yourselves. I hope you had a good class. Hopefully my son can go back to school tomorrow. It's just big old yucky pink eye, and they don't like that at school. But we should be good to go tomorrow, so I should see you guys on Friday, and I will be after school. I'll be here tomorrow, Thursday, so if you wanted to come in during Bulldog Block or come in after school tomorrow to talk about anything, I'll be available. All right? Have a good one. Thank you.